Hey everybody, so let's talk about digital I/O ports. So the PIC pins, well, 18 of the 20 can be configured for either digital input or digital output. And those 18 pins are arranged in two different ports. So ports are just groupings of pins. Um, it makes it convenient to set all the ports or all the port names in a port to a particular, or all the pins in a port to a particular setting in one shot. Um, we can also set each one of these pins individually by accessing its particular port name or bit. So we've got these two ports of those 18 pins. Let me go over here to sketching. Okay, so port A takes care of 7 of the 18, and port B takes care of the other 11 of the 18. And so um, each of those pins has a port pin name. So for port A, that's RA0, RA1, RA2, RA3, RA4, and RA5. And they're not necessarily associated in that same order with a particular pin, so that's just something we have to deal with. And then for port B, the the range is actually over 16 bits. So the register for port B is 16 bits. Let's just draw that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11, 12, 13, 14, 14, 15, and 16. Let's double count. 1, 2, 9, 10, 11, 12, 13, 14. I think I missed one there. Should be 16. So let's just go from least significant bit down here to the most significant bit. If I could draw an arrow, there we go. So the port name, or the port pins 0 through 2, those are right here, 0, 1, and 2. And then unfortunately, 3 doesn't exist. So no matter what we set that bit to, it will have no physical impact on the PIC. And then we've got RB4. I need to zoom in here so I can actually draw something. Let's see. There we go. Let's see. We actually draw. There we go. So there's RB4 and so on. And I won't go through all of them there, but we've got the RB pins that are associated to those port pin names there. So if basically if you write these 16 bits to the port B register, so this would be the binary representation of that. You could also write those bits using hexadecimal. So if you write that to port B, what pins would go to 3.3 volts? So that's our question. So everything is getting a 1. So that would be a 3.3 volt or high value, except for that pin, that one, that one, that one, and that one. So going back to which pins are associated with these names, those zeros are actually port pins RB3, which doesn't exist, RB5 and 6, which don't exist, and RB 10 and 11, which don't exist. So basically every pin on port B would go to 3.3 volts. Now you could actually write ones into these if you wanted to, but it won't make any difference. There's no physical pin associated with that. So it's a little strange for port B, but that's how you think about um, the port pins associated with each of those ports. Okay, so we're going to use those port pin names to set various configuration parameters on these pins. So let's make this a little bigger. Let's start with the configuring the data direction. So let's say, so we're deciding whether or not we want to use a digital input-output pin as either input or output. That's what we mean by data direction. So input or output. Okay. And each of those pins on port A and B are bidirectional. Okay, so the direction is set using the data direction register, or the DDR, associated with the port. So for the PIC24, the data direction is set using the tri-state adapter register, or TRIS-X, and X is going to refer to either port A or port B. So we're going to use TRIS-A register to set the port A direction, and we're going to use the TRIS-B register to set the port B direction. Okay, and so we can set each of those TRIS-A and TRIS-B port pin names to either a 0 for output or a 1 for input. And the easy way to remember this is 0 looks like O for output and 1 looks like I for input. Okay, so for an example, let's set bits 0 through 3 of port A as outputs and bits 4 through 6 as inputs. So we assign a binary number to our tri-state A register, and we set the first 4 bits. So that's RA0, RA1, RA2, and RA3 to 0. So that'll be output for those pins. And we set 4, 5, and 6, RA4, 5, and 6 to 1, which is input. So this is like setting switches to choose output or input. And instead of writing this binary number, we could just use this hexadecimal number instead if we wanted to, and assign that to TRIS-A. Okay, and remember, each one of these locations here is associated with a physical pin, which we then go back here and decide, to determine which one is set for input or output. So pin 2, physical pin 2 would be set as output, physical pin 3 would be set as output, and so on and so forth based on the switches we've set here. Okay, so that's writing. So by writing, we mean we're going to be setting a voltage, either high or low, on a particular port. Okay, let's say reading from ports. So we've set the options either write or read using that tri-state adapter. And if we want to read from port A or port B to get the pin values, or in other words, the state of whatever it's connected to, we do the following. So let's set TRIS-B to all ones. So we're setting each of those 11 physical pins to 1, which is input. And then let's go ahead and declare a variable in C. So we'll declare an integer x variable. That's a 16-bit variable. And we're going to read the voltages interpreted as either high or low using the port B register. So this is what's actually going to convert those voltages into zeros or ones. And then we're going to store that result in X. All right, so let's do an example of how to read voltages from physical pins and convert them into digital ones or zeros. So let's assume the following voltages on these physical pins. So pin 1 has 0 volts, pin 2 0, pin 3 has 3.3 volts on it. And this might be from like switches, or there's some input coming, there's some voltage on those lines, and we've configured those lines as inputs. Okay. So because of that, the digital input module will assign these particular bits as zeros for the 0 volts and ones for the 3.3 volts or high volts. Okay, so what do we get based on those physical settings, the physical voltages? What do we get when this following line of code is executed? So first of all, we're setting tris A to all ones, so that basically means port A is going to be used, and all the pins on port A are going to be used as inputs. We declare a variable x, and then we're reading in the digital interpretation of those physical voltages using the port A register and storing that in x. Okay, so port A, if these physical voltages are on those pins, then port A is going to contain 0 0 1 1 1 1 0, and that binary number converted into decimal is 30. So the variable x will contain the decimal number 30 if you inspected that variable. And I'm going to show you a little later how to inspect variables using the debugger. All right, so take-home message. All of these, if these are physical voltages on port A, and we read the values from port A using this port A register, then that's going to be the value that it exists in that variable, integer variable x. Okay, so let's look at writing to ports. So what writing to ports means is that we're going to set the value of the individual pins to either a high or a low, which is a 3.3 volts or 0 volts. So how do we set those pin values to high or low? So we use what's called the latch X register. Okay, so that's either going to be lat B for setting the pins on port B, or lat A for setting the pins on port A. And so we write a value to the latch register to set the pin values. So for example, if we want to output that binary value on port A, which means that the pins associated with these particular ports will be set to either 0 volts or 3.3 volts. So to do that, we need to set our tris A register to all zeros. So basically we're using those pins as outputs, and we can do that by setting tris A equals 0 binary, or tris A equals 0 hex, or we could just say tris A equals 0 decimal. All those do the same thing. And then we set the latch values for port A, such, for example, to that binary value or the equivalent hexadecimal value. And that will then set these particular registers, these particular physical pins associated with those port values to a 0 volt if the binary number, if the bit is set at 0, or it'll set it to 3.3 volts if it's set to 1. Okay, and you'll get those voltages on those particular pins associated with port A. All right, let's talk about shared pins. So if we go to our data sheet, you'll notice that for pin 2, there are a couple of different options here. We've got AN0 as a function of pin 2 or RA0. We've talked about RA0, that's the digital input or output function of the pin. The AN0 function is for analog input. So you can use pin 2 as either analog input or which corresponds to the AN0 function, or you can use it as digital input, which corresponds to the RA0 function. So when the analog input pin is enabled on that pin, we cannot use RA0 as a digital input. So for pins that share analog and digital functions, we have to explicitly set up the analog register for port A and port B to be either active or inactive. So that register is ANSA. If we set it equal to 0, then the digital input buffer is active. So basically we're disabling the analog input buffer and we're enabling the digital input buffer. Now I'm going to introduce this little dot function. So there are some special structures defined for every single register, well, just about every single register. And if there is a register called ANSA, then there is a structure called ANSA bits that you can dot that will pull up the individual bits of that particular register. So if we just want to set this one pin to digital input, we would set digital input or active, basically activating the digital input buffer. Then we would set ANSA0 to the value 0. Okay. Also, there are defined for all of these bits these particular definitions of which start with underscore, and then you can just use the ANSA0 bit name, and that again will access that particular bit for the register. So you can set the entire register in one shot, or you can set the individual pins on the register using the ANSA bits dot whatever or the underscore ANSA A0. And I'll show you an example to make that a little more clear. Okay, you can also read and write individual bits on the latch. So remember, there's a latch A register. So the latch A bits structure, you can dot that, and then you can set individual bits to 1 or 0. So for this one, the RA6 bit is being set to 1, which is going to output 3.3 volts on that particular pin. And likewise, there's a definition underscore latch A6 that you can use to also set that particular bit to 1. Okay, similarly, you can read values from a particular bit rather than reading an entire port using that bits structure. So remember, we have a port B register. Well, we can use the port B bits structure and then use that dot function to access the individual bits on that register. So in this case, we're dotting it with RB2. So we're just reading the value from RB2, so that'll be either a 0 or 1, and we're storing it in integer x, for example. Okay, and then you can access it directly using this definition. So this is the same. These two things are the same. They have the exact same result. So lots of different ways to set bits on ports and read bits from ports. Okay, again, we can keep going with this example, remember there's a tris A register. We can set the individual bits on the tris A register using that dot uh, structure, and this sets RA3 as input, okay, as digital input as opposed to output, and you can use that definition with the underscore as well. So lots of ways to set these things up. Let's take a look at a really handy bit of C language that allows you to inspect and also set various bits using bitwise operators. Okay, so we're going to look at the bitwise AND, the bitwise OR, the bitwise XOR, and the bitwise NOT, and the left shift operators. So let's start with the bitwise AND operator. So the bitwise AND operator says that each output bit is 1. So here's our output bits. So each output bit is 1 only if both input bits are 1. So if we're bitwise ANDing this number 1100 with this number, and this is how you would write it in C, you just say 1100 and 1010. So the result of that bitwise AND operation would be 1000, because this first 1 is the only bit that is both 1 in each of these numbers. All right, so let's look at the bitwise OR operator. So each output bit is 1 if at least one input bit is 1. So if we bitwise OR 1100 with 1010, this is the result we get. So if either of them are 1, then the result has a 1 in that bit location. Okay, the bitwise XOR is super helpful in a lot of cases, which we'll see in a bit. So if each output bit is 1, so each output bit is 1 if exactly one input bit is 1. Okay, so again, we're gonna XOR bitwise XOR 1100 with 1010, and the only bits that have exactly 1 are these two bits there, right? Because we've got a 1 and a 0, so the result is 1, and we have a 0 and a 1, and the result of that is 1. In this most significant bit place, we have a 1 and a 1. Okay, there are two 1s there, so the result is 0, and so on. Okay, you can invert all the bits using the NOT operator. So you can say NOT 1100, it just inverts them, and we get 0011. You can also left shift bits. So this just moves bits to the left, and it fills in the bits on the right with 0, and then the bits on the left just fall off the edge and aren't used. So if we shift this 4-bit number 1 space to the left, then this bit here falls off the end, and this bit here gets a 0 shifted into it. So if you're shifting a 16-bit variable, for example, then that most significant bit, which is the 16th bit, it'll fall off the edge. So it depends on the size of the variable in bits that you're working on. Okay, so that was a lot to take in. Let's look at a demonstration. Let's turn an LED on or off using some code. Okay, so most of this code hopefully will start to look familiar. There are a couple lines that don't look familiar. So we've got the ones that may not look familiar is we've got an include file here, which we'll talk about later. There's this line of code here. This is a hashtag pragma config line of code, and basically this is a preprocessor directive that is used to set up the overall PIC hardware prior to running any code in main. So these things will happen one time right at the beginning when you upload your code to the PIC, and it'll configure the PIC in a way to do certain things. Okay, for this particular line of code, configures the PIC so that we can use a debugger. So without this line of code, you can't use a debugger and step in and step through your code. So I want to do some debugging, so I've included this. And when you are done debugging, you can just do that and just disable that line. This line of code we'll talk about later. So this sets up the clock speed, which only happens once. You can't change the clock speed once you have started running your code. So these happen before any of the main code executes. And we'll be talking a lot about FNOSC, hashtag pragma config function. Okay, so we jump into our first lines of code of our main function, and the first thing we're doing is we're setting all of the registers that we might end up using in this code to 0 so that we have a known state for all registers. And so I highly recommend you do that. Just start with 0. There's our latch registers, so basically setting it to 0 sets all of the latch values, which could be used as digital output, to 0. ANS B sets port B to be used as digital input or output, so no analog. ANS A sets port A to be used as digital input or output, no analog. Tris B sets all of the pins associated with port B as digital output, and Tris A sets all of the pins on port A as digital output. Okay, so we've initialized all of our registers that we'll be using. Let's go ahead and set latch A to so that we can use input. Sorry, let me rephrase that. Let's go ahead and set latch A so that we can use pin 14 to send 3.3 volts out on pin 14. So if we go back to pin 14 in our, let's go to our, let's see here. Okay, digital pin glossary, here we go. So let's go to pin 14. You'll notice that pin port RA6, okay, that's our digital input output pin, is associated with pin 14. All right, so RA6 is the most significant bit of our port A. So that's 1, 2, 3, 4, 5, 6, 7. So that's the 7th bit is associated with RA6, and we're going to set that latch to 1, which means that pin 14 voltage will go to 3.3 volts or high, and all of the other pins on port A will go to 0 volts. And then we're going to attach an LED to pin 14 with a current limiting resistor, and that will turn so basically this command turns the LED on because it's setting that pin to 3.3 volts. Okay, so the LED turns on, and then we jump into this while loop. And I just kind of randomly picked a delay value of 20,000, and let's see what the delay function does. So this is a function that I wrote. So we jump down into this delay function, which has an input argument of an integer s value. So in this case, it'll be 20,000, and it doesn't return anything. This function doesn't return anything, so we just use void for the return value. Okay, so we're declaring a 16-bit variable k, and we're setting it to 0. And then we say while k is less than 20,000, because s is 20,000 in this case, we're going to increment k. So basically the delay function just chews up a bunch of computation cycles creating a delay. This is not a great way to institute a delay. We'll show you much better ways of using timers to do that later, but this is a quick and dirty way of just instituting a delay. So choose up those 20,000, so it'll be actually more than 20,000 cycles, and I'll explain why in a little bit once we get into debugging. Okay, so we delay, so we've turned on our LED, we're delaying, and then we're saying, okay, if, oh, actually, okay, so we're saying if, and then we have a bitwise AND operation. So remember what bitwise AND does. So it's looking for, it's comparing each bit from, so the bits in our latch A register, which are these bits, to this bit pattern right here. And it's saying if there is a 1 in both of these positions, in both of these numbers, then return a 1 in that position. If there's a 1 and a 0, return a 0. If there's a 0 and a 0, return a 0. And if there's a 0 and a 1, return a 0. So in this case, let's compare latch A, which is this value, to this value. So let's jump over here. Okay. So we have 0, B, 1, 7. Okay, so that was our number stored in latch A, LATAA. Okay, and then we have this hard-coded value of 0, 0, 0, 0, 0, 0, 1, binary value. Okay, and if we AND those, bitwise AND those, we get 0, B, 1, 0, 0, and so on. Okay, so that result of that AND is not 0. It's something other than 0. So if there's anything other than 0 in a conditional statement, the result of that statement is true. So the very first time we go through this conditional statement, the result is true. And so what we're going to do then is we're going to turn the latch value of pin 14 and every other pin on port A to 0. So that'll take the 3.3 volts and that'll drop it down to 0 volts. Okay, so now latch A is 0. And we don't go into our else statement, and we just jump back to the delay. Okay, so now our LED is off. There's a delay. And this time latch A is all 0. So if we bitwise AND that with this number, the result is 0. So that is a false. So the next time through, we'll be jumping down to the else. And then we're going to set the latch back to 1. So basically this code just toggles the latch value between 0 and 1, which outputs 0 and 3.3 volts on pin 14 with a little delay in between each. Okay, so let's go ahead and run this code. You'll have to just trust me that there is an LED on a board that's blinking over here. We won't be able to see it. That's okay. We're going to do something more interesting, which is debug this code. So we've got our hashtag pragma config ICS equals PGX3. That line of code means we can debug. We have to do one more step to debug though. We go over, let's see, where is it? We go over here and there's this little sweep icon. We're going to click the down arrow and we're going to clean and build for debugging main project. So we do that. And if we don't have any errors in our code, it will say loading complete. Okay, it hasn't started running yet. To run it, we're going to now go to this little run debug icon. So there's the run icon and there's the run debug icon. We're going to click the down arrow there and we're going to say, oops, we're going to say, why doesn't it do that? I'm just going to click that. There we go. We're going to debug the main project. So it's, okay, so now it's running. And my LED is blinking. Okay, so it's running. Because we're in debug mode, we can now pause the code and step into it. Drop this down a little bit. Okay, so we're going to look for the pause button. And before I hit the pause button, where do you think this code will pause? What's the most likely location that this code will pause? Okay, maybe you can answer that. And let's see if you are correct. So let's hit pause. And if you said the delay function, there's the highest probability that it would pause in the delay function because it's spending most of its time here just chewing away, wasting time. And then when it jumps into this, after the delay, when it jumps into this conditional statement, that happens so quickly, then we go back to the delay. Okay, so how far, let's just hover over, for example, K, and K is currently hexadecimal value 2025, and S, which was 20,000 decimal, which equates to hexadecimal 4E20. So K is less than S, so we can step and increment K. So here are the different ways we can step. We can step over with function F8. We can step into a function with function F7. So let's just do function F8, and we're going to step. So let's look at K. K is 2025. Oh, that's handy, 2025. Let's increment, and now it should be 2026, which it is. Okay, so we could just step through. We got a lot of stepping to do, or what we can do is, if we don't want to wait, is we can set a breakpoint after that delay function, and then we can just run our code. We can hit continue here, and it will just finish off that delay function, and then it'll stop at the breakpoint. Okay, so we've delayed. Let's inspect our latch. Okay, our latch value is 1, so we would expect to jump into this line of code to set latch to 0. So let's step in there. Sure enough, it does. So let's inspect latch. It's 1. Well, it's not 1. It's 1, 0, 0, 0, 0, 0, 0, which is, in fact, let me show you one other thing. So you can see, we can't see all of the bits on the latch because this little pop-up thing isn't big enough, but we can right-click on that, hit New Watch, that latch, and then I already did it previously, but then it adds it to the watch, and now we can see the entire value of latch. So it's hexadecimal 40. What is hexadecimal 40 in binary? Let's jump over here. Okay, so we have hexadecimal 40. Oh man, I absolutely despise preview. I tried to use a different app, but it kept crashing. Anyway, okay, so hexadecimal 40. So let's look at the first hexadecimal value. That consists of 4 bits. Remember, each hexadecimal number consists of 4 bits. And here's this one that consists of 4. So this hexadecimal number 0 is equivalent to binary 0, 0, 0, 0. And then this value of 4 is equivalent to 0. That's our ones place. And we've got 2, 2 to the 0, 2 to the 1, 2 to the 2. Oops, and I shouldn't have done that. That is a 1, and that's 0. So this is the bit that is associated with pin 14 RA6, right? So let's go back here. Let's go back to our code. Anyway, wait, that was a little bit of a tangent. So let's step. Oops. Let's step. So we've set latch A to 0 now. We're going to step over the delay. Okay, we stepped over the delay. Latch A is 0. So we're going to set it to 1. So right now the LED is off, and then as I step through, now I can look and see the LED is actually on now. Okay, see, this is a great way to check your code. Inspect variables, make sure they are what you think they should be. I can step through and I can slowly watch one step at a time my LED turn off and on. It's the behavior I'm expecting. Like if that LED hadn't just turned on, I would know that there's some problem with my code somewhere. Maybe I'm setting, maybe I had accidentally done this and I was latching the wrong pin, and so I would figure that out because my LED wasn't turning on. Okay. Okay, let me show you one other interesting line of code. So I am going to remove that breakpoint. Now it's kind of limited. You can only have one or maybe two breakpoints at a time. So you can't like set, all these breakpoints. It's going to say there is one breakpoint resource available. Okay, so enable this breakpoint. Okay, I'm going to say no. Okay, so let's disable those. So I'm going to disable all those breakpoints, and I'm going to set a breakpoint in my delay function, and I'm going to hit continue. Okay, now we're in our delay function. It's another little strange behavior. I don't know why it didn't stop on initializing the integer, jump past that one. It's a bit flaky, but good enough that you can use the debugger. So let's take a look at the disassembly code that this compiler created to understand better what kind of delays we're looking at here. So what I'm going to do is now this only works while you are debugging. So if while you are debugging and you are paused at a breakpoint, you can hit Window, Debugging, Disassembly, and this shows you the code with assembly comments. So these exclamation points are comments. So this shows you the actual code in C, and then what its respective assembly code is like. So you'll notice that this while loop code is actually 1, 2, 3, 4, 5, 6 instructions. Now, each instruction takes it takes one clock cycle. Let's just start there. Each of these instructions takes one clock cycle. So I am going through this while loop 20,000 times, which is going to take 20,000 times 1, 2, 3, 4, 5, 6 6 clock cycles. So this takes 120,000 clock cycles, and my clock is running at 4 million cycles per second. So you can calculate precisely how long it's going to take to run through this delay function. This is why we call embedded programming deterministic, because you can know precisely how long things are taking. You cannot do this on a Raspberry Pi with the Linux operating system. Well, let me take it back. You can, but it's not designed to do that, and it's very difficult to do that. So we call this deterministic code, or deterministic programming, or let me just call it deterministic. Okay. Now you'll notice that my delay function was the only thing I saw disassembly for. So if I wanted to see disassembly code for my main function with this while loop, I would set a breakpoint up here, and I run to that breakpoint, and then I go back to Windows, debugging, disassembly, and now I can see the disassembly code, and I know how many instructions or clock cycles it's taking for all this code as well. All right, so that's the demo I wanted to show you all. So we will just leave that paused and then go back to here. So let me show you the circuits. This is a circuit you're familiar with. I have the basic connections to just power this thing up. I've got my power with my local bypassing capacitor, and then I have I'm holding pin 1, my memory clear, pin. I'm holding that to 3.3 volts with a capacitor like the data sheet says. So this is just, these two little circuits are the minimum connections to power up your PIC. Now I have this is assuming we've already programmed the PIC and our code is sitting on there, so we would need extra connections to actually program it, but let's just assume we've already done that. The program's running here. This is pin 14, driving this LED through a current limiting resistor. Okay, so let's continue on. So as we've mentioned, every pin on the PIC is shared across multiple functions, and it's true for all microcontrollers. And typically, we need to configure which peripherals that we want to use. Okay, so I guess this slide might be in kind of the wrong place because we've already revisited this. Okay, so that's it for digital I/O, and next we'll talk about how to implement a physical switch on a breadboard that uses digital I/O.